So far we have proved the following. If M is a real symmetric matrix, then we can find n vectors that are mutually orthogonal and which are all eigenvectors of M. So there will also be numbers lambda 1 through lambda n, which will have to be real, such that M of xi is equal to lambda I xi. These numbers don't need to be distinct. There could be repetitions. So the first observation is that lambda 1 up to lambda n is a list of numbers that includes all the eigenvalues of the matrix M. That's because if there was some other eigenvalue of the matrix, then the corresponding eigenvector would have to be orthogonal to all those vectors x1 through xn. But those are already n orthogonal vectors in Rn, so they're already a basis. So there cannot be any new vector orthogonal to them. So every eigenvalue of M must appear in this list. The other observation is that although when we say that there exist n orthogonal vectors which are all eigenvectors of M, those vectors need not be unique. They could be specified in multiple possible ways. However, the corresponding sequence of eigenvalues lambda 1 through lambda n up to the ordering of the sequence is unique. So not only, as we just said, the actual distinct values have to be all the eigenvalues of M, and so they are uniquely specified, but also the number of times that each eigenvalue appears in the sequence must be always the same, no matter how we choose n mutually orthogonal eigenvectors. So let's see why. Suppose that we are looking at some other sequence of orthogonal eigenvectors. So by the reasoning above, their corresponding eigenvalues will form a list that includes all the eigenvalues of the matrix. So the distinct eigenvalues of these eigenvectors are the same as the distinct eigenvalues in this list. But we want to argue something stronger, that in fact it's not just that the distinct elements are the same, but actually that each element occurs also the same number of times. So those two sequences are the same as multisets. Well, let's say that M has k distinct eigenvalues. So let's look at them in a sorted order from the smallest to the largest. And then let n1 up to nk be the number of times that the smallest eigenvalue of M occurs in this list, and 2 be the number of times that the second smallest occurs in this list, and so on. So those multiplicities will sum up to n. And let's look at the same list of multiplicities for the sequence lambda 1 prime lambda n prime. So this would be the number of times that the smallest eigenvalue of M occurs in this list, and 2 prime will be the number of times the second smallest eigenvalue of M occurs in this list, and so on. So if these sequence of multiplicities are the same, that means that lambda 1 to lambda n and lambda 1 prime to lambda n primes are the same multiset, just maybe the order is different. But what if they are not the same? So then it means that some element will occur with more multiplicities here than here, so then some other element will have to occur with more multiplicities here than here. Then for some I, say ni will have to be bigger than n prime I. So there is some eigenvalue of the matrix that has, say, higher multiplicities here. Okay, but now let's look at the list of vectors x1 prime to xn prime. Let's remove from this list all the n prime I eigenvectors of this eigenvalue, and let's replace them with the ni eigenvectors of the same eigenvalue but from this list. So now we are going to get a new list of eigenvectors which will contain more than n eigenvectors, and those ni eigenvectors are all orthogonal to each other. The n minus n prime I eigenvectors that we didn't change, they're also orthogonal to each other. But also all those new eigenvectors that we put in the list will be orthogonal to all the eigenvectors that were already in the list, because they correspond to different eigenvalues. And so now we have strictly more than n mutually orthogonal eigenvectors, which is impossible. So that's a contradiction, and so it means that this list of multiplicities is the same. And so it means that not only what the eigenvalues are is a uniquely defined set once we have mutually orthogonal vectors like this, but also the multiplicity with which each distinct value appears is also uniquely determined. So it's just a property of the matrix. So to sum up, for every real symmetric matrix, we can find a basis for Rn just made of orthogonal eigenvectors of this matrix. And then when we look at the corresponding eigenvalues, we're going to see all the eigenvalues of the matrix. Some of them may be repeated, and the number of times that they are repeated is just some property of the matrix itself. So now we're ready to come back to that fundamental theorem of spectral graph theory. So let's say we have an undirected regular graph. We will be able later to generalize this theorem to graphs that are not regular. And let's look at the adjacency matrix of this graph. That's the matrix that in the entry ij has 1 if ij is an edge and 0 otherwise. If the graph is undirected, this matrix will be symmetric. So let's normalize the matrix according to this definition. This new matrix is called the Laplacian matrix of the graph. In entry ij of the diagonal, there is 0 if ij is not an edge and minus 1 over d if ij is an edge. On the diagonal, the entries ii will be 1. We will see later why this is a useful definition of a matrix. This is still a symmetric matrix with real entries, so we can compute the multiset of eigenvalues, which will have a multiplicity that corresponds to how many orthogonal eigenvectors of them we can find. So let's sort this multiset. So we're going to have n eigenvalues with repetitions from the smallest to the largest. So here are some properties of those eigenvalues that characterize purely combinatorial properties of J. It happens that those numbers are between 0 and 2. And then the number of times that 0 appears is precisely the number of connected components of the graph. And the highest possible value is 2, and it's achieved if and only if G is bipartite, or in the case in which G is disconnected, if and only if at least one of the connected components of G are bipartite. Well, now let's see some examples of how this theorem can be applied. So let's say we are told that there is some graph for which this is the sequence of eigenvalues with the correct multiplicities. So what can we infer about this graph? Well, we can see that it's going to be a graph with 10 vertices, because the list is of length 10. The graph is going to be connected, because 0 appears only once. And the graph is not going to be bipartite, because if it were, the largest eigenvalue would have been 2. And in fact, this is the graph of which this is the list of eigenvalues with multiplicities. There isn't a one-to-one correspondence. Possibly, although not necessarily in this case, one can have two graphs with the same sequence of eigenvalues, even though the graphs themselves are not isomorphic. Okay, so here I've taken another graph. I have computed its eigenvalues, and the list with multiplicities and in sorted order is like this. What can I say about the graph? It's going to be disconnected. It has precisely two connected components, and neither of those two connected components is bipartite. And in fact, this is the graph. Two connected components, each of them is an odd cycle. Let's see one more example. Suppose that I started from a graph. I computed its list of eigenvalues with multiplicities. It looks like this. What can I say about the graph? It's connected, and one of its connected components is bipartite. But actually, if the graph is connected, there is only one connected component. So this is actually a connected bipartite graph. And in fact, it's the 3 cube, which is bipartite.